So a neutron walks into a bar and he asks the bartender, "How much for a drink?" And he says, "For you, no charge."
Hello and welcome to another edition of Physics 262 Pre-Lecture Tutorials. I'm Dr. Steve Brule. Today we're going to be studying Kirchhoffs' laws. You just heard from legendary physicist and funny man Dusty Rhodes, and we're going to learn more about his theory of quantum humor later in the show. But first, we're going to learn how to write Kirchhoffs' loop rule equations using a walk around a circuit loop. Then we'll learn how to write Kirchhoffs' node rule equations using the what goes in must come out principle. And finally, we'll apply Kirchhoffs' laws to a complex circuit with two batteries. Well, Kirchhoffs' loop rule is that the sum of the voltages around any circuit loop must be zero. Another way to think about that is if you walk around a loop, you end up where you started. Let's apply that to an easy problem. So here's a problem we studied in our last video. We just had a 9-volt battery with 3 resistors in series. We can do a Kirchhoffs thusly. We can do a Kirchhoffs loop equation thusly by taking this little dog and having him walk around a loop. And we're just going to put the ground there just so we know that where we're starting is 0. We don't have to do that. I just did that because I thought it would be conceptually easier for our first problem. There's the dog. It's about to walk around the 9-volt battery. It goes past the 9-volt battery, and the little side of the 9-volt battery is a minus and the big side is a plus. So when it goes from a minus to a plus, we get a jump in 9 volts, a positive voltage. There's the dog walking around. He's about to walk over this resistor, and when the dog walks over a resistor in the direction of the current, we get a voltage drop of, and that's from V equals IR for Ohm's law. So it's I1R1 is the voltage drop across R1. Then when he walks across R2, we get a voltage drop across R2 of I2R2, and then the same thing for I3R3, and then he ends up back where he started, and everything is equal to 0. So that's where she started. So you go around a loop and you end up at the same voltage that you started at. Well, that seems very simple, and we didn't need to know that principle to work this problem because we worked that just using our equivalent resistances and so forth. But to solve this kind of problem, we have to resort to Kirchhoffs' loop rules. So here we have 2 batteries in the circuit, and each one of them is generating current that's going through the circuit, and we have no idea what the currents are in all those resistors. So we're going to start by writing a, well, before we write a Kirchhoffs loop rule equation, we have to assume some direction for each resistor in the circuit, a current direction for each resistor. So I'm just going to arbitrarily pick this direction for R1, this direction for R2, and this direction for I3. I should have been saying I3. And I know this one is going to be wrong because this is a strong battery and it's going to force the current in the other direction. But I want you to see what happens when you assume the wrong direction. So don't be worried about assuming the wrong directions because the equations will take care of that, and you'll just get a negative sign that will tell you that you assume the wrong direction. So when we solve all our equations, I expect to see a negative sign for I3. So we're going to, since we have 3 unknowns, we're going to need 3 equations. Well, the first thing we do before we even write a loop equation is we'll use Kirchhoffs' node rule to write a node equation because those are much easier to write. And if we look at this node right here, we apply the what goes in must come out principle, and I1 goes in, I2 and I3 are coming out, so I can just say that I1 is equal to I2 plus I3. What goes in equals what comes out. So that's a node rule. Now I could also write a node rule for this particular node. So I've got I2 going in there and I3 also going in there. So I'd say I2 plus I3, and that's equal, what's coming out is just I1. And I just end up with the same equation that I had. So I just get a redundant equation. So I can't, the number of non-redundant equations that you can get from a Kirchhoffs rules is not equal to the number of nodes, but you have to subtract 1 from that. Okay, so there we only had one node equation that we could write. So we're going to have to get the dog out and have the dog walk around a loop, and we'll write a Kirchhoffs loop rule. So here's the dog walking, hasn't walked across any voltages. The battery is a line of constant voltage, so there's no equation yet. And he's going to go from a negative to a positive, so that'll be positive 8 volts when he jumps over this battery. Then he's about to walk in the same direction as this current, so we'll see a minus 2 times the resistance. So that was, remember, V equals IR, so it's just the I times the resistance. And it's minus because you're going with the current. Now the dog went with the current again, so it's another voltage drop, minus 4 times I3, and it's our assumed direction, even though we know that it's going to be wrong. We just go with our assumptions. Now the dog's about to walk across a battery where he's going to go positive to negative, and then when he does that, he goes from a high voltage to a low voltage, so it's minus 16 volts when he jumps across that battery. And then he's back to the where he back where she started, so we say it's equal to 0. The change in voltage is 0. So now we have 2 equations, but we've got 3 unknowns, so we're going to have to write one more loop equation. So let's have our dog walk around a different loop. So here we go. She's going to go that way, and now she's going against this current. So now when she goes against the current, we get plus. So plus V, V equals IR, but we're putting RI here. So R times I. And it's positive because she's going against the current. Then here she's going to go with the current, so we get a minus 4 times I3. And then dropping down 16 volts again. And then there she is back to 0. So now we have our 3 equations and 3 unknowns, and we learned how to do this in 8th grade. So this should be really simple for you. I'm going to run through it really quick. Dr. Brühl's doggy is in the background wanting to go out, but we'll let her out a little bit later. Divide equation. So here's our 3 equations. I'm going to divide this equation by 2. So I end up with 4 minus 1I1 minus 2I3 minus 8. I divide this equation by 4, so I end up with I2 minus I3 minus 4 equals 0. Okay, so then I have these 3 equations, and I'm going to solve this equation for I1, and I'm going to solve this equation for I2. All right, so I just did that, and that's so these equations became that. And now I've got, I'm taking these 2 equations, I'm going to substitute this for I1, I'm going to substitute this for I2 in this equation, and then I end up with an equation that's all in terms of I3. Remember 8th grade? It was a good time, wasn't it? So then I solve for I3 in that equation, and I got I3 equals negative 2, which is just what we thought. We thought it would be negative because of the way we looked at it in the first place. So that means we assumed the wrong direction, but it's okay. So now I can just substitute I3 equals negative 2 into these 2 equations, excuse me there, and I get what I1 and I2 is. I1 turned out to be 0. That's all right. 0 is good. So here are 3 values, and we just want to make sure that they all work in those equations. I'll let you do that on your own. I've already done it, and they do. Okay, so here's what we got for our circuit. I1 is 0, so there's no current that's going to flow in this resistor. I2 is 2, which goes this way. And I3 is negative 2, which means the direction we assumed was wrong, so it really goes this way. So the current is really going around like that. So that's what happens when we assume the wrong direction. We just get a negative sign, and then we tell ourselves when we see that negative sign that the real current is not the direction that we assumed, it's in this direction. So it's not negative 2 in this direction, it's 2 in this direction. That's fine. And so this at first, when I did this example, I'd worked through it, and then I was kind of disappointed that I ended up with I equals 0. But it's an interesting problem nonetheless, because here we have a battery of 16 volts with 4 ohms and 4 ohms. So around this path, we know that Kirchhoffs loop rule has to work. So plus 16 minus 2 times 4 is 8. Minus 2 times 4 is another 8. So each one of these resistors has a voltage drop of 8 volts, which means, so this guy right here has 8 volts, and since we're putting a battery on here, and now his loop has to also work with Kirchhoffs loop, and since we already know this is 8 volts right here, then there's no current that's going to flow through here, because if we go up 8, down 0, down 8, we're back to 0. See? So Kirchhoffs loop rule works there. It was a lot of fun. I hope you've enjoyed this trip down Kirchhoffs loop and node rule lane. Well, it's time now for our extended interview with Dusty Rhodes with his theory of quantum humor.
So, 2 atoms are walking down the street, and then one atom says to the other, "Oh God, I think I lost an electron." And the other one says, "Are you sure?" He says, "Yeah, I'm positive."
Great! They're fantastic. So you've been researching humor in physics for how many years now?
Just under 25.
And what have you discovered?
Physicists really love bad puns, and that's about it. But I gotta say, that's my kind of humor.
And what do you intend to study in the future?
Possibly narrative jokes, but I don't see it happening. One-liners are definitely where it's at. I'm actually working on my doctorate right now.
Okay, thank you, Dr. Dusty Rhodes.
Of course. Einstein discovered a theory about space. It was about time, too.